Hello guys, how are you doing? Welcome to this day 13 of our GFG 21 day Habit Builder DSA program. I hope you guys are doing great. Quickly in the chat, we can say hello so that I know how many people are there and how many of the students who have been regular are there because I recognize some of the people. All right. Till then, you can quickly just tell me if my voice is clear and there is no lag. Hello, Srinivas. Good to see you. So this lecture is again going to be a continuation of graphs that we have already seen yesterday. We are going to be solving three more questions today, and those questions are really interesting. Believe me, you're going to love those questions. Those are some of the very classic questions of graph, and if you really like graph as data structure, you are going to love solving those problems, right? What we are going to do here, for everybody who doesn't know the concept of these videos, we have come up with an idea of delivering 21 lectures, all like each and every day till 21 days, so that you can build a habit of coding daily. And the motive is to get it is completely just to get your hand set on DSA. And we have come up to the day 13 where we are extending the discussion on graphs. And again, the pattern is going to be the same. We are going to pick up a problem. We are going to discuss the approach of it, what we can do, how we can solve it. Then we'll be taking a look at how a solution can be framed, and then we'll be coding it. This is how it's going to go. Okay, so I recognize Srinivas, then Billy, hello, and Raghu, hello. You guys are new, right? Okay, so all right. Uh, Again, to the people who are attending and who have attended yesterday as well, I would like to ask that if they had any confusion in yesterday's class, they can ask their doubts here and I'd be happy to take them. Hello, Pratik, good to see you. All right. Srinivas and Pratik are one of the regular ones, and I'm waiting for some of more people. If they join and acknowledge their attendance, then we would be just starting. All right. Till then, again, I'm asking again if you guys are clear with the basics of graph, and by that I only mean that you know graph as a data structure, how it is represented visually, and how we can use an adjacency list. If this much is clear to you, we are good to go. And obviously, it requires a little clarity upon how DFS works and how recursive calls work. That's all. Okay. All right. Uh, Billy, you answered no. What was that no for? Like, are you not clear with the basics of graphs? Okay. Couldn't try the first problem. We checked out the options you suggested, which was brush mining algorithm. We're looking to it. Great. Well, that's good that you figured out it is thousands algorithm because we today as well we have a question which is going to be solved by that algorithm. So if you have already looked into that, you're going to be again getting a better view of today's problem. It is again a complex problem, really for you that as you are new to computer programming, don't worry. We have this series from the very beginning of data structures. You can go and you can start up from the day one. All right, all the lectures are available, and the series will be continuing till the day 21st, till the 21st day. All right. Well, Pradeep, agreed. That problem is really tricky. Huh? But when you solve it on your own, you will find out how good it is. You're going to realize that, yes, what is happening inside. No worry. Again, a little part of Darsh's algorithm we are going to be discussing today as well. All right. So I believe we are good to go. Hello, one of the regular ones, Arush is here. Good evening. Should we begin? Plus one in the chat to begin the way. Plus one in the chats, please. Just give me a second. All right. Just preparing up the writing board for you guys. Fine. Let's begin with it. So, okay, I'd be dropping the link of the very first question. Just give me a second for that. Okay. So the first question is going to be very simple. It is very easy. It is for just to get you started. Okay. There is a problem. Take 2 minutes break. Then tell me what the problem is asking about. It is a very straightforward problem. It is just asking you uh, to write a code of a DFS for a graph. That's all. All right. Okay. Just go ahead. Go to the problem. Read it, and just tell me what is going to be the approach of it. You can simply write the solution in the chats because I know people are smart. And for everyone who is not getting an idea about a problem, no worries. Just take a break of 2 minutes till other people are figuring out, and we are going to be solving it. A simple DFS traversal, right? Everybody who is clear with DFS traversal, they can go like in the next tab, go and start coding it. Okay, and once the answer is submitted, you can get the acknowledgement there in the chat. All right. So for all the people who might not have gotten any idea about the question, we are going to talk about it. Let me share the question screen. All right. So here is your question, the very first one. The question says you are given a connected undirected graph. Perform a depth first traversal of the graph. Okay? And one node is given, use a recursive approach to find the deepest of the graph, starting from the zeroth vertex from left to right according to the graph. Okay, what do they basically mean by it? They're just saying that you are going to be given directed undirected graph, alright, and you need to perform depth first search traversal. And for this traversal, like most of the time, or like all the time, we have to start with the zeroth vertex. Okay, so we are given the initial vertex to start from. Again, now that once we have read the problems, you guys let's go to our writing board and see what does this. Okay, so here are we. Again, hello Ramchandra. We have this graph. It is asking that we have to begin from zero, correct? And this is one list given, and these are the vertices. We are say when we are said that v is equal to 5, that actually means that we are going to be having 0, 1, 2, 3, all these vertices. All right, I hope that is clear to you guys. And the adjacency list means, okay, well, let's right? The indices. This is what it means. 0 has these two connections, 1 has this connection, 2 has 0 and 4 connection, 3 has 0 connection, 3 has a connection with 0, and 4 has a connection with 2. This is what it is pictorially represented here, that you have your 0 here, you have 3 connections, 1, 3, and 2, right? And your 1 has only one connection 0, which is already made. The 2 has two connections 0 and 4. 0 and 4. We need to make one more connection with 4. And then we have 0, like 3 having a connection with 0. We have already established that. And then we know 4 has a connection with 2. We have already established that. So this is our basic graph that we have formed using these shapes. We are going to see how we're going to manipulate that in the code. But again, a better way of representing the same thing would be a hash map. All right, or we can say dictionaries if we are in Python. Okay, so what is going to be the approach of DFS? What is going to be the approach of DFS? Very simply, also, all the people who have been attending regularly, they can tell me in the chats what do they remember about DFS. When we are standing here, we need to explore in a single direction unless we are unable to go further in that direction. Right? So when we are standing at 0, let's say we go to 2, correct? All right. Now that we are here, very simple things, yes. Okay. So now that we are here, we have two options to go to, this and this. We are going to go to this. Okay. And this is explored. We cannot go any further. We are going to backtrack. Now, what is the second direction this we can travel to? This, right? But are we going to make this traversal? No, because 0 is already traveled the initial from the initial step. Hello Poonam, good to see you back. All right. So I hope you know how this is working. Let's see what things are we going to be passing as a parameter for a DFS. Very simple thing. We are going to be passing the node so that we can say, let's say, the node that we are currently on. We are going to be passing the graph, which is stored inside the ADJ. Then, because for the question, it is asking that we need to put the traversal in our list, and then we have to return that list instead of just printing it. So for that, let's create an answer list or any variable. It will be containing the list, which we will return in the last. All right. Once this is done, the very important parameter for your DFS post is going to be visited. And you can represent this using a set or using an array or vector of your choice. Okay, data structure could be of your choice. If you are maintaining your array data structures is going to be of Boolean type, array of Boolean values, where every index would be showing that if it is traveled or not. If it is traveled, then true. If it is not traveled, false, like that. Or else you can simply use set. And whatsoever values are already listed, you can put it inside the set. Then you can check if that value is already present inside the set. You need not to travel that again. Correct? This is how it is going to go. The very first step of is always once you enter, mark this node to be visited. Okay, mark this node to be visited. Then, because we are traversing it, we will append that to this array. We will append that to this array or list, whatever you want to say that. Pardon for that writing. All right. So I hope it is done now. Now what do we have to do? Once we are standing at a position, once we are standing here, the next thing we have to do is we have to mark it visited. Once we have marked it visited, we need to explore its neighbors. We need to explore its neighbors. What we'll say, for neighbors of neighbors of 3 in this case. What we are going to get? 2, 3, and 1. We are going to begin with 2. Again, we are going to do the same thing with 2. We are going to mark 2 as listed, then we explore the neighbors of 2, which is 4. Once we get to the 4, we'll mark it visited. We are going to check all of its neighbor. It does not have any neighbor. You go to 2, it does have a neighbor 3, but that is already visited. So that means this branch is completely exhausted. Then we will move ahead to the next neighbor of 3, which is 4 this time. Okay, neighbor of 0, I have to write. Yeah. So it is going to be 3, right? So it will say 3 is visited. Once 3 is visited, what we are going to do? We are going to explore its neighbor. It does not have any neighbor. That means return from here. And once you go to the last one, you are going to visit it. You are going to look at its neighbor. It does not have any neighbor. It will return. You will see that all the neighbors of 0 are exhausted. The program will end, and you have successfully done a TFS traversal of a graph. All right. Any confusion till here? Any of the person has any confusion till here, they can put their confusion in the chat. Ask your queries, please. Okay? Please ask queries in the chats. If you do not have any queries, we can go ahead to the code. Should we write the code? Should we go ahead for writing the code? Say yes in the chats. All right. Let's begin writing the code. All right. So what do we need to do? Very first thing, it is this is directly given as a function which is receiving v and adj. We are going to make some modifications. What? Firstly, I will use one array answer in which I'm going to be appending all the traversal that I'm making in the same like in the correct sequence, and then this is going to be the list that we will be returning as the answer to this main function. Now what I'll do, I'll create a data structure visited. Quickly, I'll create a set, right? Initially, it is going to be empty. So just get it. All right. Now, what I have to do, the next thing is, once we have created visited, we have to make up the DFS call. I'll again just write a function. What is it taking? The initial node, and we have that already said in the question that all the time we are going to be starting with 0. So I'll just pass 0, and then I'll say once I pass 0, the next thing is going to be my graph, and it is stored in ADJ, the adjacency list. The other thing would be my answer, and the last I would do is I would pass on the visited. All right. Once that is done, let's create up our DFS function, or just we can type up a return statement as well, because we believe that we will be writing a successful DFS function and the answer array will be successfully made. Thus, I'm returning it here. So now let's create up a DFS function in the global scope. I'll say def DFS. What I'm receiving, let's say the node to be I, and then I'll say ADJ, I'll say answer, and I'll say visited, right? Anywhere, if you are getting confused in the variables, you can ask me in the chat what I am typing, because some people have gotten used to the way I name the variables, and some people might be new here. So for everyone who faces any confusion in the code, or any line of the code is confusing to them, maybe because they code in any other language, they can ask me in the chats. Okay, don't be hesitant at all. All right. Then once that is done, just like what we have discussed in the notepad, what we'll do, I'll mark it visited, right? The very first thing, I'll mark it visited. I'll say visited.add. What do I have to add? I have to add I, correct? Like in the same manner, I'll append that to my answer as well. I'll append that to my answer as well. Now what I have to do, I have to explore the neighbor. So I'll say for neighbor of That's English, but we have to say for neighbor in our ABJ at the ith index. That means we'll be receiving a list because ABJ is a list of lists, and at every index we are having all the connections of that index, or we can say the node having that index value. So assuming we are beginning it, so ADJ0 will be written, and as we can see here, 231 will be the neighbors. So the for loop is going to be running on this list. Okay, I hope that is clear. Now what I have to do, I have to simply check that if the neighbor is not already visited. So I'll say if GSPOUR, if the neighbor in, or let's say not in, are visited, then I'll make a further call. GFS. This time I'd be having my neighbor, comma A D J is gonna go the way it is, and my answer array and my visited set. Everything is done. There is nothing left inside a DFS program of this particular graph. All right, it is a simple DFS. We need not make any modification to this code. Okay, let's just simply compile it. All right, that's working. All right, that is submitting too. Right. So I hope this question is clear to everyone. In the chats, say clear or say yes, it is clear. Anything. In the chats, I need responses. All right. Is this question to clear? Is this question clear to everyone? Anybody who is new to graphs? This was a very simple question, just a basic traversal of a graph. In the chats, please. All right. And are you guys coding along with me? Great, Pratik. Okay. So nobody has doubts in this question. Can we move for? Can we move ahead? People, I need more answers to move ahead. Just simply say, I have a doubt. What doubt, Poonam? Please ask it. Sorry. Waiting for a doubt, Poonam. Poonam, you need to write your doubt as well. Okay, so till Poonam is writing her doubt, for anyone else, do they have a doubt? They can also write it. I'm waiting. For moving ahead, everything should be clear till now. Neighbor in the list which contain multiple element while you are looking into a single list which is visited. See, Poonam, what happens once you enter a list and you are at the first value, assuming the first condition, you have three values inside the list, that means you have three neighbors. So once you step in the first neighbor, you will make a DFS call and you will start exploring the neighbor of that neighbor. So we will do 0, then we'll go to 2, then we'll be exploring two's neighbor, right? And once two's neighbors are exhausted, we will come back to 2, and once, okay, we'll come back to 0 because once two's neighbors are exhausted, then we will go to the next value of 0, which is your, what was it? 3 or 1? It was 3, right? Then you'll be going to 3, like that. Okay. Have you understood it, or do I need to illustrate it? Do I need to draw and show it to you how it is working, or you have understood it? Please respond in the chats. Have you understood, or do you need a written explanation? Till then, we are solving Poonam's doubt. Okay, just give me a second. Till then, we are solving a doubt. Take the link of the next question and go start reading it. Okay. Okay. Given you the link of the question. Till we are solving the doubts, go and take a look at the question. So neighbor is nothing but an element of this. Yeah. See, graph is not a different data structure like your linked list or such kind, where you create up a class and you have those elements. It is not of that kind. It is just, you can say, it is a concept, right? In this way, how you can represent data. That's all. Okay. You need not to create a nodes using a structure or a class in this. You can simply use the values. You can simply go with the values. You can use a hash map, which is like already another data structure to implement graphs. That's all. All right. Okay. So all the people, 2 minutes are going on for you to read the question. Please read the question. Okay, it's a question of an array and it's a question of yes. You can say that in a way. In a way, you can say that. Because unless you visualize in the form of a graph, you won't be able to solve that. Not at all. Okay, so people, take your time, take your 2 minutes. Okay, we'll be beginning at um, what's the time? 8:27. We'll be beginning at 8:30. Okay. Till then, read the question. Suggest me what we are going to do. What do you know about the algorithm that is the question on? Very quickly. I've put the question in the chats. Click on the link. Go to the question. Oh, so Prateek and Srinivas, where are you guys? Would you want to say anything on the question? Yeah, good Arshi. Shortest path from source to vertex. That's all. That is what this question is about. It is an implementation of Dijkstra algorithm. We are going to see the algorithm in deep. Don't worry. Okay. I hope like all of the people here have already heard about Dijkstra algorithm, if not studied that. For all the people who know about Dijkstra algorithm, write +1. For all the people who know about Dijkstra algorithm, write +1. You read about Dijkstra algorithm, you're trying to code it now. Don't worry. Again, if you get stuck in the code, we'll be doing it today. Don't worry. Prateek, knows about it. Arishi knows about it. What about everybody else? Do they know about the extra algorithm? Okay, so are there only theory or no? No problem. If you know even a little bit about it, we are going to be understanding it well. We'll do it today. And I'm waiting for like more people to interact because yesterday the class was very interactive. I don't know what happened today. A possibility is the level has gotten a little tougher, but I hope people should be interested to know about those topics. Okay. Okay, now should we start with the next question? I hope there is no need to read the question. I've already given that. It is basically just a Dijkstra algorithm, right? I'd be directly jumping upon the notepad to draw the graph and give the explanation to you. Should we start the explanation? Please write +1 in the chats. +1 in the chats for me to start the explanation. All right. Pratik has said yes. Harushi has said yes. Let's begin. Okay. Let me quickly get the example for you guys. Okay. Let me get a better example. And this is going to be a good example. All right. So let's try to see what do we mean by STR. I hope the spelling is right. What do we mean by Dijkstra algorithm? All right. Is there any H? Let me see the spelling, please. It is no, there is no H. All right. Okay. So we are going to be learning about Dijkstra algorithm. What do we mean by it? It is a single source, shortest path algorithm. All right. What do we mean by it? Before getting to know about this, let's first talk about what do we mean about weights. Okay, because yesterday I think Pratik was telling about we are not discussing the graphs with weights. So today is the day we'll be doing so. So assume if I say you have this node A and you have this node B, and again from A to B it costs you, let's say, 5, okay, to reach from A to B. Or if you want to imagine it in the form of a map, you can say A is one city, B is another, and it is 5 kilometers apart. Okay, and let's make some more. You are here at C, and this is 4 kilometers from D, and there is one direct path to C, which is just 2 kilometers. All right. So, what is the best way of reaching C? Can you tell me in what, by covering how many kilometers we are going to be able to reach C if we are standing at A? Tell me the shortest path in the chats, please, very quickly. What is going to be the shortest path from A to C? 2, correct? Correct. It is going to be 2. I want more people to answer. Okay. Yeah. A to C, 2 kilometers, 2 kilometers. Right. But when we are able to conclude that because we are able to see it visually in front of our eyes. That is how we are able to conclude that. But what if we're talking about a computer system? It is not. It won't be able to see it like this. It will be analyzing it by traversing it. Correct. And assume if you are standing here at A, and the first path that you chose, that was B. Correct. If we talk about normal DFS, assume you took this path. You traveled 5 kilometers to B. Then again, because in DFS we go on a simple path unless we have no choice, then you'll take this path. You'll reach here, and you will again give up your like you have to travel 4 kilometers till reaching here. And now all these nodes are visited, right? Now once you track back to B, you're going to be having no neighbors left. Once you backtrack to A, there are going to be no neighbors left because B is already traveled. You are not going to explore that this was just 2 kilometers. You won't be able to know that if we are talking about normal DFS. All right, if we are talking about normal DFS. Thus, we need to come up with one of the like such algorithm which will tell what is the shortest path to reach any of the vertices. Okay. Now we are going to know what do we actually mean by single source shortest path algorithm. Okay, so this was B, this is C, and here we have A. If I have, if I have said that A is your source node, again, if I have said that A is your source node, all right. If I'm saying A is your source node, I would want to know what is the shortest distance to each and every node from A. This is what we mean by single source shortest path to all other nodes. Okay, this is what Dijkstra does for us. All right. Now, do you theoretically know what Dijkstra is going to do? Do you theoretically know what Dijkstra is going to do? Yes or no in the chats, please. Yes or no in the chats, please. I'm waiting for you guys. Yeah. All right. I've got an acknowledgement from Pratik. Um, everybody else, please. Okay. So, does only Pratik know what Dijkstra is going to do, or we have other people as well? Okay. Poonam realizes it too, what we are doing. You can repeat? Yeah, surely. See, what happens is Dijkstra is for finding shortest path to all other nodes when you are standing on one node. The node that you are standing on is known as source node, which is given to you. And what you have to do, you have to figure out what is the shortest path from A to B, A to C, and A to B. That's all. Okay. All right. Now that everybody is on the same page and they know what Dijkstra is going to do, now after answering what, we will move on to how. All right. I've cleared up all the. Let's create a new graph. All right. Understanding in a deeper way. All right, this graph will be straight up a graph. All right, and now let's make some edges. Now it is a undirectional wrap. All right. All right. So I have given the weights as well. I hope this graph will answer most of our queries. All right. So now I'll simply tell you what do we do in the Dijkstra algorithm. Then we will see how we are going to implement that in the code. And before jumping onto the code, I'll tell you about all the data structures that are going to be included in this code. And we'll beforehand we'll take a look how those data structures are work. Once you are here at the source node, all right, what you will do is you will mark all the other nodes as at infinity distance, because once you are standing there, you don't know where every other node is. You don't know that, correct? But one thing you know is where you are standing, distance till there is going to be zero, right? If you're standing on zero, the distance to zero is going to be zero, correct? Now, what do we have to do? Simply, we need to go to every node. Then we need to check if they have a smaller value already written, then we are going to leave it. If they have a bigger value already written as a distance, we are going to change it. How? If you did not understand, let's see what I just said. If we are standing here at 0 and we made this choice, we are going to 2. Okay. So now what I'm going to do, I'll see that infinity is written here. I'm going to update the infinity to 3, right? Because I traveled 3 till here. Now when I have to go to this 1, okay, assume I have to go to this 1. 3 plus 1 will be what? 3 plus 1 will be 4. So I'll write 4. Okay. Then I'll travel back to it. We will see it is already listed, but we'll check what is the shortest path. And I'm doing it randomly just to figure out the distances, but it is done in a sequence. Okay, we are gonna see about that. Don't worry. Okay, okay. So once we are here, we are going to talk about two other neighbors as well. So what about this 3? 7 plus 3, 10. We are going to update that as 10. 2 plus 5, sorry, 3 plus 6, 9. We are going to update this infinity as 9. 2, 3 plus 4, 7. We are going to update this infinity as 7. 2 is completely explored. Let's talk about 1. Okay, because 1 is at the shortest distance. So now I saw that it is 4, correct? I'm reaching here in 4, and then I'll see what is the neighbor of 0. I'll see that we are able to reach 0 by adding 4 and 5. It is 9. Do we need to change that? No, because 0 is smaller. So we are going to ignore it. Don't worry. All right. And zero's neighbor 1 was also left, but we will not update the value of 4 because 5 is bigger. 0 is done, 1 is done, 2 is done. Now let's do it in the more succinct way. We are standing here at 3. Okay. 3 is at 10 distance, 7 distance, and 9 distance, 7 distance. We go with the node, we choose the node to travel next by the value of its path. Its path is 7 and it is shorter than 9 and 10. We are going to choose that. We'll see that 2 is taking, we are taking 7 kilometers still here till this node. Then we'll see what are the neighbors of this node. It is 4 written here. We are having 5 here. We will have 7 plus 1, 7 plus this one. It will be 8. Is 8 smaller than this 9? Yes, it is. This is going to be updated. Simple. All right. Now all the neighbors of 4s are exhausted. Yes, they are. Now we have two values, 8 and 10. Now we have two values, 8 and 10. We will now again see. We'll explore 5. We will explore 5. 5 is saying that I'll take two more steps to reach 10. So it will be 8 plus 2, it will be 10. We have equal values. It is not a smaller, so we are not going to update it. We let it remain 10. Okay, now again, we do not actually need to come to 3 because there is no neighbor left. Still, if you want to like go on to the iteration, you can. There will be no value updated. Eventually, we'll be having these distances, correct? 6 greater. Just quickly checking if it is correct. You guys also can tell me if there is any shorter way of reaching any of the nodes, as I might have missed. All right, you are free to make the recommendation and suggestions in the chat, so don't worry. Okay, yeah, so I believe these are the shortest path, right? These are the shortest path. So instead of going this 3 and this 6, what we'll do, we'll go this 3, 4, and 1. For 5, for reaching 2, we'll take that instead of this. For reaching this, no matter we take this or that, it is going to be same. Yeah, all right. Making a table is such easier. It is going to be. That was just an introduction at what we are going to do. Now let's do it again in a better manner. You actually make tables when you solve it theoretically in the numerical sort of questions. But let's see how we're going to do that and do those in data structures. Don't worry. Let's attempt it one more time. Solution. The approach has been messy. Don't I realize that? Oh, sorry. All right. Let's again break it down into smaller pieces and see. We are going to be using some of the data structures initially to know that every value is at infinite distance. We are going to be making an array or a list where we are going to be having these values, correct? For every value, we have 5 as well. For every value, we are going to write that it is at infinity, 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 and infinity. All right. But in the beginning, we know if we are standing at the same node, it is going to be at the 0 distance. It is going to be at the 0 distance, right? Now, we are going to be exploring 0. From 0, we can go to two paths, 2 and 1. All right. Is it clear? It will be weighing 3. It will be weighing 5. Now it is going to be the correct way of doing it. Okay, I messed it up in the beginning a little. I realize it right now. Okay, now you're gonna understand it in a better manner. Once you're standing here, right? You need to add these values. This is your U, this is your V. Again, if you want to name it like that, your initial and your final. And then you have to add these both values. What will it be? 0 plus 3. The answer is 3. Add 2. Currently, infinity is written. Is 3 is less than infinity? True. We are going to update this value with 3. Here as well, we are going to update this value with 3. Correct? Now we need to explore the other node of it. What is the other node? This one. Okay, this is your U, this is your V. You are going to add up 0 plus 5. What you will say? It is 5. Is 5 less than the infinity? Yes, it is less than the infinity. Then we are going to update the infinity to 5. Okay, and we are going to update this value here as well. We will say it is, oh, sorry, wrong one, infinity, and we are changing the value of 1 here. What we'll say, it will take 5 steps to get there. All right, I hope it is clear till now. Now we are going in a better manner. Is it fine? Once that is done, what we will do, we will also have one heap data structures. Do you know like anything about heap for everyone who is here? Do you know how heap works? Because we are going to be using that um, in this program, in this question. Right? I believe everybody knows heap. If you do not know heap, how heap works, I can summarize it to you. You just need to write no in the chats for that. Okay, write no, and I am going to be telling you how heap works. Okay, Arushi knows about it. We're specifically going to be working with min heap. Okay, so what heap does is every time you insert a value, it arranges it in such a manner. Okay, okay, Ibri, I'm going to tell you. Correct. You can store values inside a heap, and once the heap pops out a value, it is always going to be the minimum of all, either minimum or maximum of all. Either way, you make the heap. Okay. So we are going to be using a min heap so that no matter how many values we are entering and how in what sequence we are entering, whenever we are going to pop a value, it is going to be the minimum of them all, and the heap does that in constant time. Okay, popping it. So we are going to be making a like data structure like this. For that, the initial value will be the distance. Okay, the initial value will be the distance. The second value is going to be the node, like this. And once we are doing this visually here, we have to do that here as well. So for 0, it was 0 comma 0, correct? Once we define the distance till 2, it was 3. We are going to say 3 comma 2. Once we define the distance till this 1, we are going to say 5 comma 1. All right. And what do? We pop up minimum values to choose which node to travel now. I hope 0 is traveled. In Python, we are going to be like making the use of already made heap. But again, if you are like coding in a language which does not have heap present, which is just C, else in every language there is some already made data structure that you can go and use. All right. If you want to create it from scratch, you can. If you want to use the ready-made, you can. Okay. Now, once we are done with 0, that means 0 is gone. Now, which value should be chosen from here? When we'll pop, we'll get this value, having the lesser value, 3. Correct? 5 is bigger, 3 is smaller. We are going to be choosing this. That means we are talking about the second node. So the next node that we will choose will be 2. How many ways or path does 2 have? It has 1. Okay, it is beginning from 0. It has 0, it has 1, it has 3, it has 4, and it has 5. It has connection to all. Let's okay, until 2, how much steps we are taking? We are taking 3 steps. Let's mark it as 3. Okay. Okay, let me change the color of pen. And what are all the values? What are all the values that we are having? The distances that we are having already. For 0, we have 0. For 1, we have 5. For 3, we have infinity. For 4, we have infinity. For 5, we have infinity, right? And now, what are the edge weights? What are the edge weights? From 2 to 0, it is going to be 3. Okay. From 2 to 1, it is going to be 1. From 2 to 3, it is going to be 7. From 2 to 5, it is going to be 6. And from 2 to 4, it is going to be 4. Okay, I hope this diagram is clear to everyone. I've made this from this only. Okay, everything is clear so far. Just acknowledge that in the charts, please. People, once again, just tell me if everything is clear so far. Just plus one chat. Great, Pratik. Everyone else? Everyone else, please. I'm waiting for your response. Or if you have doubt, you can put it in the chats. All right, fine. Great. Now, once we have done it so far, what we are going to do? We are going to update the values again. 3 plus 3 it is going to be 6. Is it less than this? No. We are going to be leaving this value as it is. We are not going to change it. Now we're going to add 3 plus 1, 4. Is it less than 5? Yes, it is. That means we are going to update it. And we are going to update it here as well. And we are going to update it here as well. We were having 5 comma 1. Now instead of 5 comma 1, what do we have? We have 4 comma 1. Remember. Okay. Now, once we are done till here, again coming back here, 7 plus 3, it is 10. Is 10 less than infinity? Yes, we are going to be updating this value with 10. 4 plus 3, 7. We are going to be updating this value with 7. 6 plus 3, 9. We are going to be updating this value with 9. All right. We have to update it here as well and in the heap as well. Okay. So for here, what are the values? 3. Okay, for 3 we have 10, for 4 we have 7, and for 5 we have 9. All right, these are the values. Let's do it here as well. For 3 we have 10 comma 3, we have 7 comma 4, and we have 9 comma 5. Correct? All right. Now second is also listed. We can pop this from out, like pop this out as well. Okay, so these values are not under consideration now. We are working with these values. Now, what is going to be the next node to choose? Can anyone tell me in the chats? What is going to be the next node to choose according to the minimum heap, the min heap? What is going to be the next node to choose? In the chats, please. 4. Correct. It is going to be, it is not going to be 4. Pratik, the data structure is distance, comma, node. Okay, and we are seeing which is the shortest distance. Yeah, yeah, got that, got that. Okay, so it is clear that 4 is the shortest distance out of all these distances, and 1 is the node that we have to take next. Let's draw that. Okay, again, let me draw that. Okay, so what I'm going to do again, one is going to be here, one has two connections, one with 0, another with 2. Okay, this this edge has weight 5, this edge has weight 1. Correct? Now, what is the value of 1 already? It is 4. It is 4. 2 has 3, 0 has 0. 4 plus 5 plus 4, 9. Is it less than 0? No. We are going to leave it as it is. 4 plus 1, 5. Is 5 less than 3? No. We are going to leave it as it is. No changes made by 1, and the iteration is done. All right. So I hope these three nodes are clear. I'm going to erase this now. If these nodes are clear, you need to tell me what is going to be the next node that we pick up. What is going to be the next node that we'll pick up? Waiting for your answer. All right, Pratik is right. Anyone else who thinks there might be any other answer as well? Record of a clear node. The clear node. What do you mean? What do you mean by the clear node? The node which is already traveled. We need not to, because we are not going to be accessing them anytime further, because we are accessing the nodes on the basis of this priority, like this priority queue. Okay, so once that is gone, we are not going to be visiting it anyways. Because we are not doing DFS right now, so we need not to maintain a visited, because we anyways know that the node is not going to go, that we are not going to go to that node. All right. So anybody else would like to suggest that what is the next node that we'll be choosing? Because till now, Pratik is the only one who has answered. Everyone else, please. I'm waiting for the answers. And I think that Srinivas had some work to do. He left. Pratik, Poonam, I'm waiting for your answer. He has already answered. What about you, Poonam? Next node is 4. All right. Nobody else is answering. We're going to go further. Okay. Arushi has answered 4. All right, we are going to choose 4 because 7 is the lowest value of these three. 4 choose. What are the paths that we can take from 4? One is 2, another is 5. What are the distances? We are going to be seeing distances from here. For 2, we have 3. For 5, we have 9. Until 4, we have 7. What are the weights? It is 4 for this, and it is 1 for this, right? Now what we are going to be doing, we'll check. 7 plus 4, 11. Is 11 smaller than 3? No, the value is going to be as it is. 7 plus 1, 8. Is 8 less than 9? Yes, it is. This value will be replaced and the new value is going to be 8. So what I'll do, I will change this value here. I'll change this value here. I'll say this is now updated to be 8. We do not need this anymore. We will say this is now 8 comma 5. All right. This is how it is going. This is how it is going. This is also done. We have only two values left. What is the next value that I should choose? What is the next value that I should choose? Answer in the chats, please. What is the next node that I should choose? Next node is 5, correct. All right, let's choose 5. So here is 5. What are all the connections? 5 can go to 3, 5 can go to 2, and 5 can go to 4. 5 can be traveled by taking 8 steps. 3 can be traveled by taking 10 steps. 3 can be taken, 2 can be traveled by just 3 steps, and 4 can be traveled by 7 steps, right? What are the edge weights? This one is 2, this one is okay. This one is 6. This one is 6. And this one is 1. All right, let's see. 8 plus 2, 10. Is 10 less than 10? No. So this is going to be remain unchanged. Now this 8 and 6, it will be your 14. Is it less than this? No, it is not. Unchanged. 8 plus 2, 10. 7 is still less. It is going to be unchanged. No value changed. Traversal done. Okay. The last value left is 3. So let's take that 3 as well. Now we're going to be taking 3 as a node. Okay. All the connections. It has 2. It has 5. This is 5. This is 5. Now, when we are at 3, we mean the distance we want to travel is 10 till 3, correct? For 2, we have 3. For 5, we have 8. What are the weights for this? The weight is from 3 to, the weight is 7. From 3 to 5. From 3 to 5, the weight is 2. Let's update the values. 10 plus 7, 17, 17. Okay, is it going to be less than 3? No, I'm not going to change it. 10 plus 2, 12. It is less than, is it less than 8? No, it is not. I'm not going to change that. Okay, so the work is done. This is also done. The heap is empty. That is, note that, that is the termination condition when the heap is empty. All right, the heap is done. All the nodes are done. We have successfully created this array, which is containing shortest path of all the of till all the nodes. This is the end of the Dijkstra algorithm for us. Now tell me if the explanation was fine. Is the explanation well? Have you understood it? In the chats, please. I'm waiting for you to answer. Is it fine? Have you understood it or not? Cool. To in the other tab. Oh, that's great, Pratik. I hope it is running fine. And I hope the explanation was helpful. Great, great. Congratulations to Pratik. And Poonam, yes, she understood as well. What about others? We have too many people. All right. Okay, so Pratik was the one who read the Dijkstra algorithm first, but did not implement it. But now he saw the explanation of it, and he was able to figure out how we are going to implement it. He implemented it in the same way, and the code got submitted. Good work, Pratik. All right. So, do we start the coding? Like, should we start the coding? I need acknowledgement from everyone. Whosoever, great Arushi, that you understood. Whosoever is still watching, is still grasping the concept and has any doubt. Okay, sorry for those who were still reading it because I raised the stream. But if you have any doubt till now, you can put that in the chat and be happy to answer it before starting the coding. Because whatsoever I've done here, it is going to be completely the same what I'll do in the code. Okay, so you should be having a very clear understanding of what we have done here, how we have done the things, how we used heap, what we were doing. You do not have to do anything else. Okay, you have to understand the algorithm in such a way that you can code it right away. Can we move forward? Plus one in the chats if you want me to go to the coding tab and start coding. Plus one in the chats, please. All right. Okay, let's begin. The very first thing that we would need to do is we would want to convert the adjacency list to a graph, and by graph I mean and by graph I mean the adjacency list, just like we make it using a hash map. We are going to convert it like that so that we can easily use it inside of our Dijkstra function. For that, let's write up some code. Just give me a second. A Dijkstra function is written here. Okay, I need to present a string. All right, shared. Okay, I have already written this little code for you. We are going to be explaining it, and we are going to. Okay, okay, hold on. That what I shared. Date insert the value in the heap. Just coming back to you, Poonam. My screen got cancelled. Just give me a second. Yeah. Actually, I wanted to code it along with you guys. Let's code it again. All right. Just give me a second. I hope. Okay, the screen is visible. Yes, that screen is visible. Yeah. Now let me take up what Poonam is saying. We're going to update insert the value inside the heap. Yes, we have to, as well in the code, right? Yeah. Once we are getting a new distance to any of the node, that is the time we need to insert a tuple or any sort of data structure you want to maintain for two values. The first value is going to be your distance. The other value is going to be the node to which the distance is from the source node. Right? Let's code it. Okay. So first, let's see. Okay, I need to increase the size of. Okay, is this size fine? Is this size all right? You can type okay in the chats. Okay, let's go now. So as I said, before moving ahead, I'll make up a graph. Before moving ahead, I'll make up a graph. For that, I need an empty dictionary. I've created that. Okay. Thanks for clearing the doubt. Pradeep. Yeah, I was set. So what do I need to do now? I need to traverse all my edges, all my vertices. So for that, I'll simply write for I in range v. V is the value till what we have the nodes, right? Okay, done. Now I'll say graph. At the ith key of the graph, what I'll do is I'll simply I'll simply create a list because we'll be needing a list, right? So I'll just shoot a list constructor. So till now, what has happened? I have created a graph in which we have all the nodes as keys, and corresponding to all the nodes, we have empty lists. Okay, so this is done till now. Now what I'll do, I'll fill up the values. I'll say for I in range B, for I in the okay, it is going to be capital V. I in range V, again we are now this time we will be traversing the adjacency list that we have received as a parameter. Okay, so what I'll write, I'll say oh, graph. This will give us the empty list, and I'll say what do we need to do? We need to add the list present at adj I to the empty list so that it will be inside the graph as well. Okay. So after this, what will happen? Completely, we'll be having a graph, like we'll be having the adjacency list in the form that we wanted to, in the form of a dictionary or a hash map. Okay, is this code clear to everyone till now? Till here? Till here, is this code clear to everyone? Hmm? In the chat, please. Great. Now what I'll do, I'll create a function say I'll say is shortest path. Okay, I'll say shortest path. And what parameters is it going to take? This is going to be the source node, so I'll send S. It will be needing the vertices, so I'll send V. Definitely, we need to send graph there, right? And all the other values, we can take care of all the values inside the, I mean, all the data structure, the list that we'll be maintaining for the minimum values, I mean the minimum distances, or the heaps, we can do that inside the function. We do not need to create it from here, then send it in the parameters. We can do it there, no worries. Okay, and what do we expect this function to do for us? We expect this function to return us a list, which is actually going to be the distance list that we drew just before, and that was containing all the shortest distances from the initial point, from the source node to all the others, no other nodes. So once we receive that list successfully from this function, what we'll do is we'll simply return that list, because that is what this question requires as an answer. All right, now let's code it up. Again, I'm going to code that in a global scope as usual. AF. All right, just because we would want to make the names easier, I'm gonna say instead of S, let's say source. Just capitalizing it. We have three things that we needed. First, we are going to be using the inbuilt heap. I'll just say import heap queue. Okay, and let me just say heap queue as H Q. All right, as H Q. I'm going to be using the inbuilt heap. All right. We need not to take a fuss about how we are going to do that. Very first thing that we need to do, we need to create an array. And what do we need? We actually are talking about priority queue. Yeah. Just for that short PQ, I've created one list. Now I'm going to create a heap out of it. Okay, how heap is created? Heap takes in a value and heapifies it. So if we already have an existing list, we can use the function heapify that is present inside your heap queue like completely convert it into a heap. Or if we are starting from scratch, that means we'll be building the heap from scratch. We just need an empty list to start with. So this is the list that I have created. Now this list will be acting as a heap, and all the heap functions will be applicable to it once we pass this list as a parameter to the heap functions. First function that we would need, see, initially, because what we have to do, we know that what is the distance from source to source? It is 0. So we have that 0 comma 0 uh, ready for us to put it inside the heap queue, put it inside the heap. So let's write it. HQ dot, the name of the function will be heap push. Heap push. All right. Heap push. What do heap push do? The first parameter is the list that we have created. The other parameter is the thing that we have to put in inside the heap. It is not just a single integer; it is a tuple. What is that? 0 comma source, src, because source may vary. We cannot just go with the first example and write 0 comma 0. What do we actually mean is 0 is the distance if we are standing in the source and we have to reach the source. Okay, so it's 0 comma source. All right. Once this is done, what is the next thing that we have to do? We also have to create a list, which is your or we can say distance. Now, what I'll say, I will give infinity values to all the existing indexes, or you can say the nodes. How I'm going to do it? I'll simply write float, right, float, I say inf. Well, this is a way you can represent infinity in Python. You have different ways of doing that in different languages. All right. and I'm going to multiply it with v. This is going to make, this will just create up a list from 0 to v minus 1 with every value to be infinity at the beginning. We are going to change it further. Okay, so the first thing that we have to do, we have to take the 0th element, because we know as per the question we'll always be beginning with 0. Okay, so what we are, okay, sorry. SRC. Let's write SRC here, because the source could vary. We are writing a general function. We are not sitting like sticking up to the question. It is saying, all right, I'm messing up. We were beginning from 0 in the previous question. Here we are going to be getting a source. Done. Clear the issues. Correct. All right. Distance from the source to the source is going to be 0. Always correct. The distance from the source could be anything. We are going to mark it as 0. Has everybody understood it till now? Because I had a little confusion that was coming from the last question. I hope that was not a confusion with you guys, or if it was, it is clear. Is the code till now clear to everyone? Is it? Is it clear to everyone? In the chats, please. I'm waiting. It is clear to Pratik. Line number 5. What we have done, I cannot illustrate it on this screen. See, why enter 0? Because if you are standing at the source and you have to evaluate what is the distance from source to source, it is going to be always 0, right? If you are standing in a classroom and you are being asked that what is the distance till that classroom, what you would say? 0 distance. You are already standing there. Correct. That is what we are saying here. Have you understood, Poonam? All right, Arushi has understood it. People, I need more responses, please. Now Poonam has understood that as well. Okay, okay. Would anyone else other than Arushi, Poonam, and Pratik like to respond here? Anyone else? Well, I believe there are not enough likes in today's video, so I believe the likes are worth it because the explanation was pretty tough. All right. So if you guys are understanding it clearly, just press the like button. I need the likes to be increased. Yes. Great. All right. So I hope everybody has understood the code till now. Let's proceed. Okay. So what are we going to do now? We are going to actually get the values from the heap, because that is what we are doing. Initially, we are going to get the 0 comma 0 as per our example, because that is the smallest value, and from where we get the smallest value, we get it from min heap. So I'm going to do hq dot heap pop. This is the function. It will pop the minimum value from the heap, and what you need to like serve as the input, you need to provide the list that you created, the priority queue, PQ. All right. I hope it is clear. Once you have gotten these, once you have gotten these variables, you have your distance, you have your node, initial node. Now what you are going to do? Now again, we need to check for v comma gst. Let's say rate is in the graph g r a p h graph q. All right. Now what are we checking? We are checking the neighbors of. We are checking the neighbors of the node u, and quickly we are putting the values of the neighbor inside v and weight separately, uh, because this time the graph that we have created, it does not have the value of the node. It also has the weight. What is the weight? The distance needed to reach that node. So what we have done, we have our keys, and in front of the keys we have list, and those lists like have tuples, and every tuple is composed of the node, comma, its weight. All right. I hope I'm able to make this clear to everyone who uses Python. They know those, like that tuple is getting unpacked here, but what we are like actually doing here is, for everybody else, every tuple that you have, that could be, let's say, 5 comma 3. That means 5 distance is needed to reach 8. Sorry, if 5 distance, okay, sorry, again, let's change the values. If we say that 2 is the vertex and 8 is the weight needed to reach there, that means we are standing at 0th position. Assuming we are standing at, let me write it here. Assuming we are standing at 0th position, and we have 2 as the, okay. As we have, okay, we have 2, we have this edge here, and this edge is, let's say, it has 8 as a weight. Okay, so this is how it is going to be. This is how it is going to be represented. Inside V, we are going to be having the next vertex, and inside weight, we are going to be having the distance, right? I hope it is pretty clear to everyone. Thanks for saying that, Poonam. Now, what we'll do, we will check that the distance, if the distance that is of V, we have already created the distance array, and currently for the first iteration, it has all the values to be 0. And um, once it is what? Once it is greater than the distance that we already have in U, where we are standing, plus the weight, plus the weight. This is the case, then what will we do? We will simply update the distance, right? We'll say dist B, the dist V equals dist U, yeah, dist U plus weight. Simply the thing that we were doing there, if the all like mentioned distance to reach a particular node is greater than what we have calculated, we'll just replace the calculated value with the greater one, so that we are finding the shortest path. All right. Now what do we need to do? We need to say HQ dot we push. We need to again push the new tuple that we create, right? Just like we were doing there. So I'll simply say what we have to do. We have to say keep push again. What do we need to push? We need to say the first parameter is a priority queue, the list. Again, the next is going to be the tuple. Tuple will be test v, because we're talking about the destination node, comma v. All right. Once this is done, what we'll do, we will simply, okay, firstly, this is how many times this is to be done. Okay, how many times this is to be done? Would anyone like to suggest that? How many times this is to be done? How many times we will be doing the code from line number 13 to line number 18? Because we have to do it again and again. I am asking about the termination condition. When we will stop? When we will stop? I'm waiting for the answers. And if you did not get the question, you can ask me in the chat to repeat the question. People, till the time we have neighbors in the list. All right. We have once all the neighbors are exhausted, that means correct, until all the nodes are relaxed. Okay, you have read the theory, you know the terminologies, got that. until the heap is not empty, right? Until the heap is um, still containing some value. Once the heap gets empty, okay, we are going to stop. So I can simply say while while my P queue, the priority queue, the list that I'm working on, while it is there, we are going to be working. Once it gets exhausted, it will be broken. The code will be completed, and we will return. What do we have to return? What did we promise in the main function that the shortest path would be doing? It would be returning as the list. So we are going to return the list just from here, because now that this list is fully created and it contains the shortest path to all the nodes, right? Have you understood it till now? Have you understood it till now? Because the code is now completed. Okay. All right, all right, all right. I think today's class is a little tough because people are coming and then going. All right, now let's just see if it's working fine. Oh, SCR. I have messed up my typing somewhere. It is SRC. Pilot. All right, it's working. So for that, yep, it is. It is passing all the test cases. All right, fine. Now again, the code is written on the screen. Does anyone have any confusion on any line? They can ask me right away. Okay, I'm going to increase the size of it, yeah, so that you guys can see. Yeah, this is the code. Ask me if you have any problem in the code right now. I'm waiting for you guys. Or if it is clear to you guys, you can mention that yes, the code is clear. Now I know how I can implement the extra algorithm using a priority queue. Okay. Okay. And after this, we're going to be moving ahead to a very interesting question. A really very interesting question that is going to be completely shaking your brain. How the things are going, how things were done. Again, I'm not going to be doing it completely for you, but I'll give you some hints and I'll explain you the question. Okay, great. I hope like how many people are here, they are completely understanding each and every aspect of our code and the explanation, right? Right? Plus one in the chats for confirming that. Plus one in the chats, please. All right. And Sarushi. Yeah. So now we know. Let me stop sharing the screen. Okay. So, other than the questions that we are doing, in general, you just joined Chandan. Chandan, so what we're doing here is we are solving like questions, three questions daily. So I hope you might know about the 21 days series. We are on the 13th day, and the topic that we are doing today is graphs. Okay. Okay, I'm understanding the concept plus algorithms. So that's Python, a little bit difficult, but when I go in Java, okay. All right, fine. So should we continue? Should I give you the link to the next question? What do you guys think? Let me bring the link. The name of the question is strongly connected components. And here is the link of it. Go to the questions, go to the question, give it a read, and tell me what do you understand by it. Okay, and it is going to be working upon a very famous algorithm called as Tarjan's algorithm. All right, we'll see. We'll take a glimpse of that algorithm and how it is working. Actually, the yesterday's third problem, the articulation point, also was revolving around the same algorithm. Okay, and again, I'm going to give you the similar hints, but a little more. All right. Take 2 minutes break. Read the question. In the chats, tell me what do you understand by the question. Once you have read the question, just mention that in the chats that you have read the question, and we'd be going further. Okay, Pratik asked something. What was unfocused or Dijkstra? Well, it is, let's say, let me tell you. See, what happens? It is going to be you are going to be going to every node plus you're going to be doing the find the SSD. Yeah, Arush. Now, yeah, it has V plus we are going to be on the edges, and for every it is going to be comparable to log V. Yeah, so it'll be V plus E log V. Okay, V are your vertices and E are your edges. This yeah, this is going to be once we're using priority queue. All right, and the other things will be neglected because that operation is just V times. Yeah. Okay, so Arushi has answered to find the SSC in the graph. This is what we have to do in the next question. All right, let's see the next question. A very difficult question. Well, first, let's jump on to the writing area. Share screen, window, share. All right. First, let's talk about what are connected components. Yes, Arushi has stated the correct thing. Good. Now we are going to be seeing how it will be done. I'm going to be giving you the hints, then you have to figure it out on your own what is going to be the proper way of coding it. All right. Now let's talk about graphs just like this. Just normally, let's talk about it. Try to imagine it. We might have multiple connected components that form a graph, right? If we are having a node, okay, let's say like this. If we have this graph, okay, and this is a node standing alone. If this is the whole graph, okay, how many components does it have? See, in Kosaraju's algorithm, you need to make multiple DFS calls, and in Tarjan's algorithm, what you need to do is the work is done basically in one DFS call. That's all. Okay. Yeah. How many connected components do we have? We have three connected components. Correct. How we can figure out what could be algorithm to figuring out the connected components? Tell me. What could be simple general algorithm to find out the number of components? Because if you are given this, what you have is you have a adjacency list, and you might know how many vertices are there. So if I name it one, two, change the color. One, two, three, four, six, seven, five, eight. Okay, every node should have two edges. Okay, this node does not have any edge. Then, then what? See, you have you will be having it in this format, correct? You will be having your graph in this format. Visually, you just saw that it has three components. You answered me three. But how are you going to figure out that it has three separate components? How are you able to say that this has three separate components? Please tell me. Please tell me. Any idea, any way your mind is working in, whatsoever we have learned so far in graph, if you want to apply that here. Exactly, exactly, Pratik. Pratik always gets it completely right. Great. That is what we are going to do. Lovely. So what will be done is we can maintain a visited array, right? We can see 0, 1, 2, 3, 4, 5. We can visit every array and we can mark true. We can visit every node and we can mark true. Okay, so what we'll do, we'll call upon DFS. We'll just use a loop and we'll call upon DFS. We'll call upon DFS. And what is going to be the condition? That if the node is not traveled, if the node is not traveled, that means if the node is not invested, just make the call. And for every call, we will increase a counter, right? We'll declare a counter. We will increase the counter every time we make this call. Once we make the call to three, it will completely visit this component, right? It will completely visit this component. So once we have made a call to zero or three or any of the node in this component, all the nodes in this component will be traveled. Okay. In this case, this was the thing. Zero was not even included. Okay. So in this case, in the first iteration only, all these will be marked true, and all the further ones, I am writing the index above. Okay. All the things will be like this. Wait a minute. Uh, all right. Okay. Yeah. So every other thing is false till now. Now, once you're going to iterate through this array, you'll see 1 is already visited, 2 is visited, 3 is visited, 4 is visited, 5 is not visited. This time you're going to make a call to DFS and you're going to increase the counter. Okay. The same thing will be done here for 5. Once you go to 5, this will be traveled, this will be traveled, this will be traveled. This is still false. Okay, the next iteration is going to be here. You will check that if 6 is already visited, you will say no, 6 is not visited. We'll again call the DFS, increase the counter, and eventually we are going to return the counter. It will give us number of components. Clear, right? Clear. Clear till now. Is it or is it not? Clear till now. Is it or is it not? Till now, is it clear or not? In the chats, please. All right, great. But this is not going to work for our question because this is the what we have discussed. It is for undirected drafts. Okay, this is for undirected drafts. Simply, it is not going to work for the question because that is for directed drafts. All right. So this is not the time to ask the question. We'll keep the question for the last. Okay, for the last 5 minutes of the session. All right. Okay, so what we um, just studied was for undirected drafts, and we are talking about directed drafts in the question. We need to come up with a separate approach for this for the directed drafts, right? Now, what are SCC? First, let's discuss that. Also, for that, let me take up an example. Let me take an example. Let me look for a good graph for you guys. So, a graph could be like this. Okay. All right, all right. I made a graph. Just give me a second. All right. Yeah, it is a good example. So, if we draw a graph like this, very simple graph. Fine. One, two, and three. When can we say, when can we say that it is SCC? When can we say that? The definition is if you are standing on any of the node and you are able to go to any other node of that component. If we are standing at 1, we are able to go to both 2 and 3. If we are standing at 2, we are able to go to both 1 and 3. If we are standing at 3, we are able to go to both 1 and 2. Okay, where you are standing, you are able to travel to all the other nodes of that component. If such component exists, we say it to be SCC or strongly connected component. Do you understand the definition of it? Do you understand the definition of it? Guys, do you understand the definition of it? Yes or no in the chats? All right. Yeah. So before moving ahead to giving you a glimpse of Tarjan's algorithm, some of the terminologies are really important. Again, the similar terminology that we discussed yesterday that I just gave you little hints about. Let's see that in a little depth. Okay. First is discovery time. Again, two arrays needed to be maintained. First is discovery time. Another is you can say lowest discovery, like lowest time to reach that. It is again your array. All right, you can create a data structure for that, which may look like second. Right. Okay, the diagram is really messy. Okay. Now, what do you mean by discovery time and lowest time? People who were present yesterday can answer that, and I would want to hear that from them in the chats. Just type it. What do you know about distance time and sorry, discovery time and the lowest time? Very quickly. very quickly. Tell me what is discovery time and low time. If you have no idea, you can simply write I don't know. Okay, if you have no idea, you can simply write I don't know. I'll be telling it. Correct. Arashi has stated it correctly. What is discovery time? Time at which the node is encountered. Okay, for one, it is 130 distance times where we reached where we first reached it. Correct. What about the low time? Where what is like low time is the possible lowest time that we can reach that node in. Don't worry. Let's The definition is lowest time, as it is already saying, it is the lowest time to reach any node. That's all. Okay. Because to reach a node, there might be several paths. And if you're not talking in terms of your distance, we can talk in terms of time. So if we had chosen a different path, we could have reached one node earlier. That is what lowest time tells us. All right. So if we have to talk about the lowest time of these for one, okay. We also we are not talking about the real time. We need to take time ourselves. So let's initialize it with zero. So for the first node, it is going to be zero zero, correct? For the first node, it is so we decide the source arbitrarily. Yeah, we do. Like for this, okay, talking about the algorithm, we are not going to be defining it arbitrarily, but all the time the graphs are given in form of a list, and they believe that all the indexes are nodes. So again, we are going to be choosing. We are going to be according to the list. We are going to be going according to the list. The first value is going to be zero, then it's going to be one, then it's going to be two, and the similar way we are going to be calling a function just from the zeroth node, and it will go and travel and tell us what are all the other nodes. All right. And if that is not a case, if that is not the case with all these questions, then the source will generally be mentioned. So that from where you can traverse the whole graph. But that wouldn't make any change. No matter if you choose any other graph, if you choose any other node, then again the algorithm is gonna work fine. All right. If you talk about okay, Kosaraju, we don't have much time for that. But if you talk about Kosaraju, so what happens is you do DFS in the normal graph, then you do DFS in the inverted graph, and then you draw the conclusions from there. And what is an inverted graph? When every edge is completely like made the opposite. If the edge is going from 3 to 1, it will be made 1 to 3, and that will happen for each and every edge. Okay, so that will be your inverted graph. You take the DFS of both, and then you see, then you compare the things, and then you get to the conclusion. That is what we do in Kosaraju. We need multiple DFS operations. We are discussing Tarjans here, and I'm just going to tell you the necessary things about Tarjans, and you are going to be exploring that algorithm on your own, and you're going to be writing the code for that. All right, okay, where did my diagram go? Here it is. Let's see. One word answer to your, so we can decide source arbitrarily. Any node you decide, you would be getting the number of components. All right. I Okay. So yeah, we were discussing discovery time and the low time. 411 that we have reached here, we know it is 00. For 2, what is going to be 1 second? Okay, time is going to be constantly increasing. So for this, it is 1, right? For this, it is 1. So it is going to be this discovery time 1 and uh, travel time, sorry, low time 1. For 3, it is going to be increased to 2. Okay, discovery time 2, low time 2. Correct? We can go here, but we cannot come from here. And again, we'll check. For 4, what is the thing? We are going to compare. What is it already having a lower time? Yes, it is. Do we need to make it 4? No, right? That means this will be remaining unchanged. But if we take a bigger graph, and there is one option that there is one node who has a lower value to be, let's say, 8, and you are having the lower value to be for here to here, your lower will become, let's say, 4. Okay, then the values will be changed. Okay, so you are going to be keeping the lowest value inside this. Okay, I hope you understand me. This is what our discovery time and low time are. I want to tell you about two more terminologies. Just give me a second. Okay, once these two things are done, you should know two more things. You should know two more things. That one thing is back edge, back edge, and the other thing is cross edge. Do you guys know about what these two terms mean? Do you guys? I'll do that again, Arushi. After that, all right. She knows what back edge and cross edge means. Do anyone needs an explanation on back edge and cross edge? Anyone? Does anyone need an explanation in back edge and cross edge? Right. All right. Okay. If you're talking about if we are going in this manner, all right. If you're going in this manner, we are going from one, then two, then three, like this. So we can say that this is actually a back edge because we are going from ancestor to its descendant, like that. If we have this ancestor and descendant relation, then those are the back edges. And if we talk about cross edges, and cross edges are just present between two nodes, like this. It does not have any ancestral connection. Okay, let's talk it. Let's call it one. This is 1. Now this will be a 4. And further on with moving ahead with the graph. Okay, between 2 and 3, it does not have any ancestral and descendant connection. That means it is a cross edge. And for 3 and 4, we can say that this have a back edge because this has ancestral connection. Okay, ancestor and descendant. If this is a possibility, then those are back edges. If that is not a possibility, those are cross edges. All right, you understand that? Do you understand that? Yes or no in the chats? No, there is no connection between crosser and a bridge because a bridge completely divides a component into two, right? Cross edge could be like we cannot say it to be a bridge. Simply. We are not talking about trees here, Arshi. So there is no way like we can figure out the level of the levels basically. All right, fine. Okay, now what you guys need to do is simply I'm gonna just write a very rough algorithm. Okay, all right. While backtracking, what you guys do is you update the low value. I'm just writing this algorithm so you would be able to figure out how it is working when we dry run it. All right. So, taking a simple example. Okay, now can anyone tell me in this graph that I've drawn how many strongly connected components are there? How many strongly connected components are there? Yeah, I'm waiting. I'm waiting. Can anyone tell me in this graph that I've just drawn how many strongly connected components are there? Again, let me repeat the definition of SCC. Somebody asked it. Whenever, what is a strongly connected component? A strongly connected component is one in which, where no matter in what node you are standing, from there you are able to go to each and every node of that component. All right, three. All right, let's see if Pratik is right or wrong. Who agrees with Pratik? Who trusts Pratik and agrees with him? Or is she saying there is only one connected component? All right, and everybody else? Everybody else? Okay, Poonam is also saying three. What about others? I want more answers. Again, there are only three people studying, and everybody else is just watching. Fine. Let's see if it is one or three. Okay. Every is saying it is one. Read Pratik. Fine. Again, again, I'm going to tell about SCC. What is SCC? If you are standing at a node and you are able to go to each and every node of that component, then that is a strongly connected component. Any individual node, okay, can also be called as a strongly connected component. Okay, whosoever has answered one or them, let me ask a question. If you are standing at three, if you are standing at three, are you able to travel all the other nodes? If you are standing at three, are you able to go at one? No, you are not. If you are standing at four, are you able to travel all the nodes? No, you are not. Correct? Okay, so Arushi has realized that the correct answer is three. Now, what are the components? Let's see. If you are standing at zero, you are able to go to two and you are able to go to one via this path. If you are standing at one, you are able to go at zero, you are able to go at two, right? If you are standing at 2, you are able to go at 1, you are able to go at 0. That means this is a strongly connected component. Now, if you go to 3, can you go to 2 or can you go to like 1 again with this 3? No, you cannot. That means this is again a separate, strongly connected component. Again, going with 4. That means like you cannot go anywhere from 4. You cannot go even to 3. So that means this is this is a third strongly connected component. This is the algorithm that is used to find out how we are going to get to it. Okay, so the data structure that we made, it is going to help us in that. We have to create discovery and low arrays like this. We have to make up the values whenever the value of your um, whenever the value of your what we say that your discovery time and your load time are same, if these two values assume are same, and there is no possibility to make a further call, that means there is no possibility to go further. You have no node to travel. Just in the case of 4, if you have no further path to go, you check that if the discovery time and the load time of that are equal. If that is equal, then that is your uh, and that till that is your strongly connected component. You also have to maintain a stack. Okay, I'm giving you so many hints. Okay, I've made this data structure, I've made this data structure, I've written this for you, I've made this diagram for you. You need to figure out things on your own, right? In this question, you are supposed to be. I'm giving out a lot. You have to maintain a stack. Once you make calls, things are going to be going inside the stack. Okay, like this. Things are going to be going inside the stack. So assume you are here. You have traveled. You went to 0. Okay. You put in 2, then you put in 1. You again came back. You changed the path. You put in 3. You put in 4. Okay. This is done like this. All right. Just what I've said. I put those in the same sequence inside our stack. All right. Once you have reached 4, believe me, once you go to 4, it is going to be see, 0, 0. It will be 0, 1. Sorry, 1, 1. It will be 2, 2. And this will be 3, 3. This will be 4, 4. For 4, you will be going to 4, 4, right? And for 4, you have no further way to go to. You check if the discovery time equals to the load time. Yes, for 4 it is. Then you are going to pop all the elements till 4 because 4 is at the top. You're just going to pop 4. Then 4 is individually your strongly connected component. Once 4 is popped, that means the work of this is done. Then you go back, then you backtrack. Then what you do? Then you backtrack. And while backtracking, you update the low values. Okay? You're going to backtrack to 3. You're going to see if the low value can be updated. For 3, it won't be. Again, the values will be 3, 3. Then again, you have to pop out the elements till 3 because 3 is in, okay, because 3 is what? 3 is your, 3 is at the top, only 3 will be popped, right? And 3 will again be your new strongly connected component. And again, in this stack, once you backtrack to 0, the values will be updated, and the low value will be the low value of 2 and 3 will be 2 and 1 will be updated. And once you again go back to 0, that will remain 0, 0 only. That means 0 is the connection of your strongly connected component. And again, you are going to come to the stack and you will see. Actually, you can also see if a package node is present there, you have to update the low value. And this is a package, a package, right? This is a package. Once you backtrack to 0, this is a package that you have. You need to update the low values. Once you update the low values as written here, what you will do again, 0 is the value you need to pop till. Okay, in the stack, if these are the values, then the last component, the last strongly connected component you have is going to be 0, pop like this. All right, then you'll have your all your strongly connected component. Well, how low is updated? I can tell you, but I wanted you to do it yourself. But okay, the low, wherever you are, you have to compare the current low with the low of the with the distance of the other node. With the distance of the other node, you are going to compare the low of your current. This is how it will be done. You'll be maintaining this data structure. This is how you will be. This is how. This is, yeah. Okay. Low. The current low is updated with the minimum value of your current low and the distance of the node that you are traveling to. All right. This is the formula. Now I have told you a lot about it. If if I had to tell the whole algorithm, I would have. But I need to hold back some of the things. You need to figure out how things are working and how this stack will be controlled. You need to see if you need a visitor or anything. That is up to you how you're going to implement it. All right, you need to do some research because then only you will be able to code it yourself and you will be feeling how the Tarjan's algorithm is working. All right. So I'm going to be ending this here. But as we do, we remain for 2 minutes at the end to talk. So anyone who has any question, they can put on in the the question could be about the series or in general. If you want to ask anything, you can here. Well, again, from my side, it was really great interacting with you guys about Prateek, Arushi, Poonam, and this time the last person is not here. But let's see. I hope you guys enjoyed the series. You are still enjoying the series. I had the 5 days that I had to take. Today is my last day. From tomorrow onwards, there is going to be a new mentor that will be taking up newer topics. I really enjoy teaching you guys. You like many of you were completely continuous in the class. You were interacting too much, and I had fun. And for the reciprocation, if you want to appreciate, do comment down because that is same is there just in front of you? See, go to Geeks website. You are going to get an article for everything. All right, you can find it for that, and you can get a proper roadmap to learn graphs. All right, no worry. You can simply go to the practice section, and you can put down the interview questions there, or you can simply go to the go to the filter where you can filter it according to a company. Have two filters in the questions, graphs, and the company name. You will get the questions there. All right. Okay. So again, mentioned today is my last day. It was great teaching you guys, and I hope you also learned what I was trying to convey. And the sessions were great. I would like to hear your feedback about it in the chats. You can nobody can give your views. Pratik is the only one constantly giving me the comments there. I really appreciate that, and I always go and like it. And for all the other people, I ask the same. The number of likes is still very low. No matter what you guys do, I want it above 100 till tomorrow. All right? Share it with your friends, give it to other people, okay, to watch, make this video useful for them as well. I need that increased. All right, and the comments as well. No matter what you guys are saying here in the chats, I want comments in the video as well. All right. Yeah. Thanks, Poonam. Thanks, Arashi. Thanks, Pratik. Thanks, everyone else in the stream. Thank you, Ibri. And all right. Hopefully, we'll be meeting again in some new series or in some other video from Geeks for Geeks. This was the end for me for this particular 21-day series. Thanks a lot. I'll be ending the broadcast now. Okay. I would want to say bye in the chat. I'm saying bye. In the chat, you can reply to me, and I'll be ending it. All right. We're still waiting for byes. Okay. Bye, Pratik. Goodbye, Akshay. Bye, Poonam. Good night, everyone. We'll be meeting sometime soon. Yeah. All again, if you guys, anybody who has not able, like who has not been able to ask their doubts here, they can get connected to me in my link list, and they can in my LinkedIn, and they can go there and ask me anything else they had in the series. All right. See you guys. Bye.